In this work, we present DeepOPG, a framework to summarize findings in orthopantomograms using weak supervision data that is easy and quick to annotate for clinical experts. Orthopantomogram, OPG, or dental panoramic image, is an imaging modality aiming to be the first-line dental screening tool. It covers your maxillofacial region with a half-circular scanning and compresses the anatomical structure into a two-dimensional image. Dentists interpret OPGs quite a lot for the purpose of understanding treatments done on the patient's teeth, and however, the interpretation suffers from low inter-rater agreement. On top of this issue, it is not straightforward to communicate the results with patients due to the lack of real-time assistive tools. An automatic tool to summarize findings in OPG would not only help increasing interpretation consistency, but also ease the communication with patients by displaying the visualization in real time. In the clinical workflow, it also assists dentists with the treatment decision process, and the summaries can be logged into a data registry for subsequent data analysis. One big challenge for existing works is that they don't cover features that are highly requested among dentists. The system has to be versatile enough to detect the teeth, number the teeth, detect implants, and derive the finding summary. To add value to the system, we furthermore incorporate dental knowledge to refine system outputs so that the results are coherent with dentistry. We also leverage weak supervision that is fast for dentists to annotate, but effectively boosts the performance of DeepOPG. Here's an overview of the DeepOPG system. There are three essential modules within. The input OPG first goes through the functional segmentation module to derive a functional map of 7 classes. The segmentation map is then concatenated with the input image to go through the tooth localization module. Since the output of the localization module will potentially contain more than 32 teeth, we utilize the dental coherence module to subselect from the detected objects. As the last step, we combine the segmentation map and the tooth instance map refined by the dental coherence module to produce findings for each tooth. We use a ResNet50-based UNet as the functional segmentation model and MICCAI as the tooth localization module. We want to highlight the dental coherence module since most of the time researchers directly apply deep learning models to medical data without considering its inherent structure as a prior. Hence we, at inference time, perform optimization to select the best assignment of objects to teeth by maximizing the dental coherence reward as described here. It turns out to be a generalized quadratic assignment problem widely studied in optimization theory. It is also a hassle for our dental experts to annotate all the per pixel maps for learning the models. Hence, we're interested to see if we can annotate the presence of teeth in each study only and leverage that as a training signal. Coincidentally, the dental coherence reward is somewhat compatible with that pursuit. Concretely, we sample an assignment matrix at training time and use the ground truth weak supervision to derive the reward. With a sample probability and reward function defined, we can easily optimize with policy gradients from reinforcement learning. This reinforcement learning process acts as a fine-tuning step after the tooth localization module is first trained with densely annotated data. Finally, as the last piece of the puzzle, we combine the segmentation and the localization outputs. For every tooth, what we're interested in is the fractional area of each functional component. Using the area not only allows an interpretable finding summary, but also allows you to freely adjust operating points for those binary classifications. We use this Brazilian OPG dataset and enriched it with our annotations from 3 board-certified dentists. We annotated localization, segmentation, the weak summary for training, and finding summary for testing. A primary evaluation endpoint is the AUC-ROC, and we plotted here for 6 finding types across all teeth. The AUC-ROC is high for all finding types, but is especially higher for those findings with clear imaging traits on OPG. To validate the effectiveness of our proposed components, we perform an ablation study by stripping out some of the features. We find that our weak supervision indeed boosts the AUC-ROC while only constituting 1% of all annotation efforts. Components such as dental coherence decoding and feeding segmentation maps into a localization module all help the DeepOPG system learn better. Ultimately, it is imperative that we compare our results to prior works on different tasks. While the data is different from work to work, we make sure the evaluation metrics are identical and the data quantity is roughly similar. As you can see, in many clinical tasks such as tooth segmentation, natural tooth detection, or implant detection, we all reach satisfactory results in comparison with previous works. In conclusion, we demonstrate a performance system called DeepOPG that summarizes findings well in OPGs. Specifically, this is achieved by 3 modules and a novel supervision data modality. The data and code will be released to inspire further research in this area.